Yes, I talked about how we had some appetizers over the past few days. And today we're going to start the main course of the course. We're going to spend a lot of time over the next few classes learning about what a derivative is, how to differentiate functions. And before I get into the nitty-gritty details, I'd like to give you a little overview, see why this thing we're going to learn about is so important. Why we're going to spend so much time on what seems like an odd exercise. We're going to be looking at curves and try to find the tangent or the slope at some point on them. So if you will let your imagination go for a minute. Imagine you're going to drive to LA and you're going to take the fast route. That's I-5. Zip on down. It's pretty straight. It's a little scenic, not all that scenic. If you want scenery, you go down 101, or you can go down Route 1. That takes a long time, it's really beautiful. But you can fly down I-5. You can go 70, I think the limit is 70. You can go 80 and you don't even get much attention from the police. So you just want to get there fast, and you're going down this highway and you're bored. Maybe your radio's broken, your iPod. And you're looking at your dashboard here, and you have 3 pieces of information. You have more, but you have a speedometer, right? Tells you how fast you're going. You have a clock, tells you what time it is, or if you care to use it that way, how long it takes to get from one point to another. And you have your little odometer, right? Wheeling off the miles. So, since you're a little bored, and you're inclined, you got nothing else to do, you're watching these, and you keep track. And you notice that after about 10 minutes, which is 1/6 of an hour, you've traveled 15 miles. So, you know your velocity formula, or at least we'll call it your VA, your average velocity. It's just 15 miles over 1/6 an hour, or, whoa, we're averaging 80 miles per hour. Now, at the same time, you're not using cruise control. And the speedometer is kind of going up and down. It's going at like 75, 85. And if you were to chart this is the speedometer here, you'd see it would vary a little. So what we're really measuring here, this average, is this is distance traveled, time, right? What we're measuring here is this red line, this average. And if we look at the slope of this red line, we find that, yes, we're going 80 miles per hour on the average. Right? So what's going on here now? How do we kind of correlate what we're seeing on the speedometer with this graph? Well, if we were to take just a short little distance, 10 seconds, we could kind of see an average across maybe 10 seconds. If we have really, really fine equipment, maybe 1 second. But what we're getting here is this tangent that we're going to be so obsessed about in this class. It's actually the slope of this tangent here. So that's one way to think about what we're going to be learning. I was going to say, both of these measurements, the instantaneous velocity at each moment or this average, they have uses. Instantaneous velocity is really useful if you want to keep getting a speed there, right? You want to keep it definitely under 80. But if you want to know how long it's going to take you to get to LA, how much time left, the average is actually much more useful. All right. So, we're interested in, finding the velocity at each point along here. We call that differentiation, or finding the derivative of our function here, our distance with respect to time. If you have an explicit function, like a polynomial or a logarithmic function, we can do this analytically. That is to say, we can just play around with the function. We don't need actually data points to get this derivative. And over the next few days, we're going to find all sorts of useful ways to take a function, all sorts of functions, complicated functions, composed functions, and find the derivative. Now, all of this is about, in a sense, finding a rate, right? A rate of change here. And this is not just useful for driving down to LA. There are a lot of real-world examples you may run into. So, first one I'm going to mention. Anybody here like pre-med or life sciences, biology? Okay. So, in medicine, you come up with a pill, right? And you give it to try not to laugh, right? I'm not an artist, it's just, here. This is a person who takes a pill, right? And you want to know how that pill is absorbed, right? So, you find some way. You either use some theory of absorption, what you know about quickly the stomach acids, go after this pill, gets it to the blood, and then your body removes it. So you're probably going to see something like this, right? It takes a while to get up to some peak, and then eventually it kind of trails off. And you want to know about this curve. One of the things you want to know is, like, at some point you get below the amount of drug you want in the system, and you want to know, well, so how often do I have to administer this drug to keep it at some level that I want? So you will need to know calculus. Okay, I'll bet that we have a few business majors here, economics majors, people interested in money. Now, you may have you may have taken a little economics already. You may not have, but one of the things that economics and business people need to kind of keep track of is the flow of money, right? I mean, you know, people get money, you put it in the bank, right? And then what does the bank do? It gives it to other people, right? But we're not allowed to give it all away. We have to hold on to some of it. And the federal government actually decides that. And one of the things they're concerned with is how money is flowing through the economy. You know, what rate? If you let money flow too fast, does anyone know what happens? Inflation, that's right. If you kind of pull back too fast, you can put the country into a recession. So although we've seen kind of in the last year or two, we've seen this amazing phenomenon. The government just threw huge amounts of money into the economy, trillions, and yet we didn't get inflation. Well, we had a problem. It's called COVID, and it affected commerce enormously. So you know, it's complicated. But again, it's another example where you know the rate, you know how the rate changes is going to be important. Maybe some of you are science or physics majors, maybe chemistry. Chem majors are going to need a little physics, right? And you'll be studying fluid mechanics. And fluid mechanics is just, you're watching fluid go through, I don't know, it could just be out in the ocean, it could be going through a pipe. And you have a certain amount of water coming in, at a certain pressure, the pipe changes size, things happen, right? So again, you know, this calculus is going to come in handy when we're trying to calculate what to expect. One of my own favorite examples that I got to use a lot. Sorry, Mr. Betts. Second grade, Mr. Betts used to come in with our teacher, some papers, hand them out. You're supposed to draw scenery. Mr. Betts says, "No hairy sons." This is what a hairy son is. And Mr. Betts had a terrible sense of humor, but it was okay for second graders. He said, "Do you know what's worse than a hairy son?" Two hairy sons, yeah. Okay, so inside a star, you have a core, and nuclear fusion is going on, and energy is moving out. And, well, you don't really see that. We don't have much evidence of what's going on there. We just have some physical equations, and they tell us, well, gravity is pulling the matter in, and that creates pressure. It's a gas, and it heats this up. And at some point, you get nuclear fusion, and then energy starts moving out, and it again pushes back against gravity. So the sun is kind of what we call a steady state. It's like at any given point, you know, the pressure in and out has to, it only differs by as much as the energy flow through it. So lots of calculus in astronomy. I'm sure, you know, whatever you're studying, you know, you're here because they want you to have this background, so there's going to be some use for it. All right, so let's go right to where do we go here? But we're going to start looking at derivative at a point of a function. So we have some function. I'm going to make it easy to draw. And we have some point A, and has some value, f of A. And we're interested in, this tangent at that point A, and in particular the slope, delta y over delta x, right? Well, as an approximation, we can pick another point. We can pick a point, we'll call it, what do we call it? I guess we're just going to call it x for the moment. All right? Now, if I were to give you the coordinates of these 2 points, if I were to say they're x1, y1, and x2, y2, everyone would know how to calculate the slope of this line going through it. Right? Would be, you can do it either way, but it would be y2 minus y1 over x2 minus x1, or vice versa. So we're going to come up with an approximation for our slope. We're going to use this notation. We're going to put a, what is that? It's not an accent. It's a, yeah, thank you. It's an apostrophe. And approximate at the point A is the y-coordinate, it's f of x, minus the coordinate of A, which we'll call f of A. And then we have x2 minus x1, which is just x minus A. Well, we have this x at some point here, but really what we want to do is move that x closer and closer. And now we're going to find that subject we started with limits useful. Because really what we want is as x approaches 0, f of x minus f of A over x minus A. This is a definition of our limit at the point. This is a definition of our derivative, or our slope, at the point A, as we let x go to 0, right? Tangent just slowly kind of gets right into place, or the line gets right into place until it's a tangent. Now, we're not actually going to use this formula very much, because there's a more convenient way for our purposes. Instead of thinking of A and x here, we're just going to think of this distance as h. And then this point is still f of A, but this becomes A plus h. And we're going to think of, as we move x here, h goes to 0. So the formula we're going to use, which is equivalent, yes? Speed speak up, because I'm not hearing you through your mask.
When x goes to 8?
Yes. Thank you. Remember, do I owe you 2? I'm going to bring it in next week. I wrote myself a note. Okay. So instead, we have this formula. F prime of x equals, now it's f of, well, we're not going to use a anymore because this is going to work for any x, right? X plus h minus f of x just over h. There we go. The limit is h approaches 0. That's our definition for the derivative of a function. All right, well that's kind of messy looking and it's not clear how we're going to use it yet. But we're going to have some examples. Before we do, I just want to digress for a second. I think I mentioned that this notation, the f prime, this comes sort of from Newton. Sir Isaac Newton, he put a dot over it, but this became this apostrophe. There's another notation that was developed in France, and we're going to see it a lot. So I want to mention it right now. Instead of writing the derivative of f of x this way, we could write it as d dx f of x. Or we might see it as df of dx. And since we often we're talking about like a graph where the function is the y-coordinate, you'll often see dy dx. Now, again, we don't want to think of this as, well, you can think of it as like a fraction, but it's not a fraction, it's notation. The implication is here you're dealing with very, very small y's and very, very small x's at some point. Infinitely small, where we get a limit. But it's not a fraction, so be aware of that. Okay. So, as part of our definition, we say the function is differentiable if this limit exists. We've seen some functions where, we've seen some limits that do not exist. And if you don't have a limit there, you don't have a derivative. It's not differentiable. Okay, we're going to take a real example. You'll see it's not all that tricky. It's not all that hard. Let's just take f of x equals x squared. So we'll write out the derivative, f prime of x equals the limit as h approaches 0 of f of x plus h, which is just x plus h squared, minus f of x, which is x squared, over h. All right, well, we need to do a little algebra. This is x squared plus 2xh plus h squared minus x squared over h. We want the limit. Well, this is kind of handy. The x's cancel. And again, we can take out a factor here of h. So now we have the limit of h over h times the limit of 2x plus h. You know this limit, right? This is going to be 1. And again, this is just a polynomial. As h goes to 0, it's just going to go to 2x. So we have that the derivative of this function is 2x. All right. Well, if all of our derivatives work out to be that easy, we're in luck. We're gonna do this again now with an even easier limit. This is a kind of a sanity check. What about our linear friend f of x equals mx plus b, right? Although that's just the line, the y-intercept at b at a slope m. Well, we can think ahead. Obviously, the derivative should be a constant function m. The line has the same slope everywhere, but let's give it a shot. Let's see what happens. So f prime of x will be f of x plus h, n times x plus h, plus b minus f of x, which is mx plus b, all over h, and squeeze in here the limit as h approaches 0. All right, well, again, some algebra, mx plus mb plus t minus mx minus p. I'm sorry, this is mh, right? Over h. My b's cancel. My mx's cancel. And now I just have a limit, again, as h approaches 0, of h over h times the limit as h approaches 0 of m. Well, this is obviously 1. This is constant. It's just m. Well, that's what we wanted. All right. Let's move into some scarier ground here. Let's look at the function f of x equals square root of x. Before we get going on this, just think about what that looks like. Its domain starts at 0 and goes to infinity. We're not doing complex calculus yet. It kind of moves off, but whatever it starts with, whatever the slope is here, it's going to decrease. So we'd like to see that in our result. It never gets to 0. So I think it might approach 0. So let's apply this machinery again. F of x, f prime of x is going to equal to the limit as h equals to 0 of f of x plus h, that's the square root of x plus h, minus square root of x over h. Yeah. That h and this h, we're not quite sure what to do with that, are we? All right. So if you've been playing around with algebra enough, you might have a knee-jerk reaction here. That'd be a good one. Think of that pattern. A squared minus b squared equals a plus b times a minus b. And think to yourself, well, this is the a and this is the b. I know how to get an expression with just these squared, right? So I want to multiply this by the square root of x plus h plus the square root of x. But to get away with that, I need to make this into 1, right? Which I can do easily. Right. Well, this looks promising. And I still have a limit here to worry about. Square root of x plus h minus x times the square root of h plus x, that's a plus b, that's a minus b. That's a squared minus b squared. It's x plus h minus x. Oh, that was nice. Well, nice on the top. At the bottom, we've got h times the square root of x plus h. We didn't get rid of the square roots completely, but maybe we can deal with them now. Well, the x's cancel. I've got an h on the top. So again, this is going to be limit as h approaches 0 of h over h times limit as h approaches 0 of 1. That's all I've got left. Square root of x plus h plus the square root of x. Okay, well, this is 1. What's going to happen down here? Well, h is going to go to 0. Right? So we're going to have 1 over square root of x plus square root of x. That's just going to be 1 over 2 times the square root of x. So that's our derivative. Now let's see if that makes any sense. What happens at 0? As we move this way, x gets very small. It's like our slope is getting more and more horizontal, or vertical. So we don't actually have a derivative at 0, do we? Infinite slope. But as we move this way, x gets bigger, kind of slowly, not as fast as x, but it gets larger and larger. And so the slope gets smaller and smaller, and asymptotically this goes to 0, which is just what we expect. It never gets there. Square root of x keeps getting bigger forever, but ever more slowly. All right. Any questions so far? Some of you may have seen this before. All right, we're going to do one more of these. One we've done before, but we didn't use calculus. Remember, in first class, we asked about, well, we have this function. Minus x squared, which, well, we played around with it and we found that this is y. When we square both sides, we end up with x squared plus y squared equals 1. Just the graph, it's a circle. This function is a little more limited. It's just the top half of the circle. And we found a function that at 0 is 0, and at either endpoint, 1 and -1, and to infinity. Just using geometry, right? Well, let's apply calculus now. See what we get. Approach 0 of, okay, so f of x plus h is the square root of 1 minus x plus h squared minus f of x, 1 minus x squared over h. See, we're going to need room here. So, anyone have any thoughts on strategy on how to go after this one? We have that same problem, right? These ugly square roots we want to deal with. We've got an h under there somewhere. How do we find this limit? I have to manipulate it somehow. Yes?
When we use the same thing as we did for the last problem.
Well, we could try. That's how you find out. That's how you do problems in math. You get an idea, you try it. If it doesn't work, think of something else. All right, so I'm going to leave off the limit for now. Just imagine it's there. We'll save some time. So, thank you. So what do I want to multiply this by? Square root of 1 minus x plus h squared plus the square root of 1 minus x squared. Okay, that's our a plus b to our a minus b. But again, you have to keep things proper. So here we're just multiplying by 1. And, all right, the algebra is a little more complicated, but I have to put this down. My strength here. So we're going to have 1 minus x plus h squared, square root squared, minus 1 minus x squared, the square root squared, over square root of 1 minus x plus h squared plus square root of 1 minus x. All right, let's move that over here. So on the top, we can do a little fooling around here. 1 minus x plus h squared, that's x squared plus 2xh plus h squared. And minus, all right, I'm just going to take the minus sign in. This is going to be 1 plus x squared. And let's see, that's 1 minus x squared minus 2x minus h squared minus 1 plus x squared. And our 8x squareds disappear. Okay, that's good. Our 1 disappears. So we end up with negative, we're going to take out the h, the negative h, 2x plus h. And now I better get back my denominator. Okay. I better pick up my notes. What happens next? Yes? Oh! Thank you. I knew I was missing something. Yeah, there's an H here, and an H here, and an H here. All right. Oh, well, that's good. Now we have limit. I might as well bring out the minus H. And what do we have left? 2x plus H over square root of 1 minus x plus H squared plus square root of 1 minus x squared. Okay. So now it gets pretty easy to see what's going to happen. This H is going to go to 0. We're going to end up with 2x. This H is going to go to 0. We're going to end up with square root of 1 minus x squared plus square root of 1 minus x squared. So we have 2 times the square root of 1 minus x squared. And we get a minus sign from here. We can cancel our 2's. And so way back here, our derivative becomes negative x over the square root of 1 minus x squared. I think if you look at your notes, you'll see that that's what we found geometrically. Right? I mean, it's 0, it's 0. Right? And as you get close to either 1 or minus 1, it's going to phase off to infinity. All right. All right, so we've got some mechanics here. Useful mechanics for finding the derivative of a function. We want to look at the distinction for a second. I guess I'm going to write it back again. I'm going to write our derivative formula. So I said this derivative has to exist. We'll see that in order for this to exist, the function has to be continuous. Has to be continuous near f of x, because otherwise you're not going to have a limit there. Again, it doesn't, as in all limits, it doesn't matter. Well, it does matter here for this. You do have to be continuous at x. So continuity and differentiability are related, they're similar, but they're not exactly the same. And I want to take a look at this function, f of x equals the absolute value of x. So if I graph that, it's going to look like this. Well, you can see on 0 to infinity, open interval, it's just this straight line. Slope is going to be n. Yes? Yes. I'm gonna have to go buy some more. Hope you like chocolate. Just put in your order. Okay. Also, from negative infinity to 0, again we have a straight line. But what about here at 0, x equals 0? You kind of see that coming from this direction, if we're finding this limit from this direction, we're going to get some m. But from this direction, we're going to get minus m. We don't have a limit. And in fact, if you try and think of what would a tangent at this point be, well, it swivel around. It's not really any one value. So while a function has to be continuous to be differentiable, it's not sufficient. There's something else here. If you have kind of spikes in your function, it's not going to be differentiable there. I think I have time for the break to torture you with a proof. That's probably what it is. Probably torture. Make a statement like that, what you want to keep in mind is the important thing is the theorem, not the proof, right? You won't have to reproduce the proof. Okay, so the theorem says if f is differentiable, let me get this right, at x, then f is continuous at x. So while just because a function is continuous, that doesn't mean it's differentiable. Would you do me a favor of kicking that little cat my way? Yeah, all right, thank you. Well, the fact that a function is continuous doesn't mean it's differentiable. If it's differentiable, it is continuous, or at least so says this theorem. I don't know if this is entertaining, but like if you get really interested in math and you take an analysis class, they managed to come up with a function, find a function where it kind of, it's spiky, but it's somehow it's spiky everywhere. I mean, I'm not drawing it quite right because you can see places here that it's definitely differentiable. But you can create these aberrant functions, really interesting, that are they're so crazy, they jump up and down, they're continuous. They're not like that rational, irrational, where you're jumping from point to point. It actually is connected. It's continuous. And you can prove that, and you can prove that you can't find the derivative anywhere. That's fun. Okay. So first, we're going to, before we do the proof, we need a lemma. Does anyone know what a lemma is? Okay, a lemma is just a theorem, just like the theorem we're going to try and prove, but it's a little theorem that we need for our big proof. So the theorems, the lemma says if f is continuous, then limit as x approaches a, wait a minute. I'm sorry. The lemma is f of x is continuous. Since we only need half of this, I'm only going to show half of this, but if and only if the limit as h approaches 0 of f of x plus h equals f of x. Okay, this looks a little like our definition of continuity, right? With continuity, we say, well, as x approaches a, f of x will equal f of a. Looks a little like that. Here we're saying we have some point x, and our limit as we get close to it, as our h goes to 0, is that, if it's continuous. So we start with the fact that f is continuous, which means that the limit as x approaches a of f of x equals f of a, right? That's the definition of continuity. So we let x equals a plus h. We're just doing a substitution here for x. So that means that we just substitute that in here, the limit of a plus h, as a plus h approaches a, f of a plus h will equal f of a. Right, so I just put in x here and here. So now we have to think of, what does it mean that a plus h is approaching a? How can a plus some value approach a? Yes?
Each is being equivalent, but a is getting smaller and smaller.
Yeah, so h is going to 0, right? It's the same thing. I'm saying the same thing. Saying h approaches 0. So the limit of f of a plus h equals f of a. Right, but I didn't specify what a is. A could be anything. So I can just rewrite this as the limit as h approaches 0 of f of x plus h equals f of x. All right, so from the fact that f of x is continuous, we find this result, which is what we wanted. Fine. Oh, your torture is relieved for a few minutes. Take a break. Come back and we'll finish this up. Any more homework? Like most of them. Does that work okay? Okay, are you all ready? Okay. So getting back, we want to prove that if f is differentiable, then f is continuous. So we start noticing that if h is not 0, then f of x plus h minus f of x is equal to f of x plus h minus f of x over h times h. I'm explicitly saying that h is not 0, so I can write this. I'm just multiplying by 1, right? Well, let me take the limit on both sides of this. I guess we need a limit here too, right? All right, so we should recognize this, right? What's that? Just derivative of x. We know that limit exists because we said f is differentiable. Right? That's the premise. Well, clearly this is 0, right? Limit is h approaches 0, 0. So we have that limit is h approaches 0 of f of x plus h minus f of x equals 0. Well, that tells me that the limit as h approaches 0 of f of x plus h is equal to the limit as h approaches 0 of f of x. Well, that's our lemma. If this is true, then f is continuous, right? So we've shown right here using lemma. So f is continuous. Yes?
How did you get from the bottom of the board over there to the top of the board up there? I'm a little confused.
Oh, okay. So this is a separate proof. Okay? What we want to show is f of x is continuous if and only if this statement is true. These statements are reversible, so it's, it's an if and only if. Right? I just transformed our definition of continuous into this statement.
Okay.
So here, I take this this expression. I start with h not 0, so I can write it this way. But then I can find a limit on both sides. Well, the limit on this side is the derivative, which we know exists, right? But the limit over here is 0. So this is 0. So we know that this limit has to equal 0. But if this limit has to equal 0, then we know that the limit is f of x plus h as h goes to 0 is the same as the limit as h goes to 0 of f of x.
Okay.
Right? Well, I guess you can see this doesn't matter, right? But that's what our limit tells us. It tells us that means it's continuous.
Mm-hmm.
So any function we have that is differentiable, has a derivative at some point, is continuous there. That will come in useful. Again, this is not an advanced math class. Not be responsible for doing proofs like this. It's just, sometimes it's nice to see that, I'm not just pulling all this stuff out of my hat. Okay, so a few days ago, we started looking at limits, and we had some continuous functions, and we started putting together a toolkit of things that we knew the limits of. The limit of a constant, things that are continuous, like polynomials are continuous. And now what we're going to do is we're going to build a toolkit of derivatives. And it's going to consist of two things. We're going to have some derivatives we know. We'll have some basic derivatives we know. Maybe a little more general than the ones we've seen so far, and we'll have a set of rules that we can use to create new derivatives. So it's, it's a little like Lego, you have some blocks, you can put them together and you can make things, and then you take those things and put them together. Create something more complicated. All right, so I'm just going to enumerate here some derivatives we know. For f of x equals some constant, the derivative is an easy one. If I have a graph of a constant line, the slope everywhere on that line is 0. F of x is a line, mx plus b, and the derivative of x is
M.
Earlier today, we saw that f of x equals x squared, and f prime of x, remember, 2x. The 2 here and a 2 here, that will come in handy. And we saw f of x equals square root of x. Derivative is negative 1 over 2 times the square root of x. And finally, circle, we have 1 minus x squared. Derivative is negative x over square root of 1 minus x squared. So, if every time I came up with a new function, we had to use the formula, the limit. Formula f prime equals x plus h minus f of h, x. I'm going to get it right this time. I always forget to leave room. Limit as h approaches 0. if every time we had to use that, it would be kind of awkward and time-consuming. So we're gonna need some rules to simplify things. So the first rule we're gonna look at is the derivative of the sum of two functions is the sum of their derivatives. Now, we have a bunch of rules. We're not going to prove all of them, but some of them are just so straightforward. We want to take a look. So we're going to start here with the definition of f plus g prime of x. That's the limit as h approaches 0 of f plus g at x plus h. This is, I hope that's not unclear. This is f plus g here is the function which consists of adding the two functions. Right? If I had f equals x cubed, and g equals the cosine of x, and f plus g is just a function x cubed plus cosine of x. It's pretty straightforward. Okay, minus f plus g at x over h. Well, we're just going to rewrite what this means. This means f at x plus h plus g at x plus h. That's what this means. Minus f of x and minus g of x over h. Well, we can rearrange this. This is f of x plus h minus f of x plus g of x plus h minus g of x all over h. Well, remember we had a limit law, right? The sum of the limits is the limit of the sums. So this, of course, is the limit as h approaches 0 of f of x plus h minus f of x h plus the limit h approaches 0 of g of x plus h minus g of x all over h. Well, what's this? This is the derivative of f of x. And this is just the derivative of g of x, which is what we wanted to show. Similarly, but even easier proof is that some constant times f at x, the derivative of that is just the constant times the derivative at x. Now, if this notation obscures this, but I'm just saying I have some function which is, if I create a function by multiplying it by a constant, then I don't have to refigure out its derivative. It's just the derivative times that constant. Constants can move in and out. And we go about it the same way. K times f, well, k times the function derivative of that is the limit h approaches 0, k times f of x plus h minus k times f of x over h Well, I can take k out of here, right? I can take it outside the limit because that's a property of limits, right? Constant times the limit is the limit of constant times the function. So it's just k times the limit. This is just the derivative of the function again, right? So it's just k times the derivative of the function. All right, now here we get to an interesting rule. I guess I should try and enumerate these. Okay, now those of you who've taken calculus before, no spoilers, please. What we would like is a formula or a rule for the product of two functions, f times g, derivative of that x, in terms of the derivatives of f and x. Now, wouldn't it be nice? Wouldn't it be nice if the derivative of f times g of x was just the derivative of f times the derivative of g? Yeah, unfortunately, it ain't so. But it's a nice, easy rule anyway. Anyone want to take a guess? Thank you for not spoiling. All right. Turns out it's f times, carefully, f times g of x is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. Oh, not so bad. It's nice and symmetric, and it has to be. Anyone see why it has to be symmetric like that? Well, if I multiply f times g, is that any different from multiplying g times f? No, it's the same. So whatever this is, switching f and g has to get me the same thing, right? All right, so let's go for it. Let's see if we can show that this is the case. So f times g, derivative of x, is the limit as h approaches 0 of f times g x plus h minus f times g x all over h. Which, rewriting it a little nicer for our purposes, f times x plus h times g times x plus h minus f times x, g times x. All right, what can we do with that? Well, this is one of those moments in math where the professor just kind of pulls a rabbit out of a hat, says, do this. Let's try this. I'm not going to say why until we see if it works. What we're going to do, we're going to add f of x plus h times g of x. Well, we can't just add it, right? We have to change it. So we'll subtract it also. That works, right? It doesn't really change things, does it? Okay, so now we're gonna, these are all over h, so we're gonna rearrange the terms here. We're gonna have f of x plus h times g of x plus h minus this guy over here, f of x plus h times g of x. And now we're going to take these two guys that are left, but they're both minus, right? So I'm sorry. Use these two, right? So, is that what I want to do? No. I don't want a minus. Just has let's make sure I don't lose another trouble on this one. X plus h times g of x minus f of x g of x. Okay, that looks great. Let's fill in the limit here. Okay, let me factor this. F of x plus h times g of x plus h minus g of x over h. And then here, I'm going to factor g of x. F of x plus h minus f of x. And the limit of the sum is the sum of the limit, so I can separate the limits here. And the limit of the product is the product of the limit. So let me rewrite this all the way over here. Well, this is the limit f of x plus h times the limit of g of x plus h minus g of x over h plus the limit of g of x times the limit of f of x plus h minus f of x. Okay. Well, the limit of f of x plus h as h goes to 0 is just f of x. This nice construction here should look very familiar. This is the limit as g of x plus h minus g of x over h as h goes to 0. That's just derivative of g of x. Similarly here, we've got g of x and derivative of f of x. So that's our proof of the product rule. here has not run into a word jumped out of my head. Proof by induction. Who here has not seen a proof by induction? Raise your hand. Everyone has seen, okay, you haven't seen a proof by induction. Okay. You may have, but maybe you haven't heard today. So, let's say I was looking at the sum from n equals 0 to, so I'm going to use I here. I equals 0 to n of I. Well, what do I mean by that? Well, okay, a little chart. So if n is 1, the sum is 1. N is 2, the sum is 3. N is 3, the sum is 6, right? Or it's 10. Okay, so I think, well, how do I get this sum from n? Like an expression for it. So I could use kind of the Gauss method, say 1, 2, 3, all the way to n, and then write it backwards, n minus 1 all the way to 1. Add them, n plus 1, oh, n plus 1. Okay, so I have n times n plus 1. Oh, but I have it twice, so it's that. Okay, so I have my formula now. But I want to prove that this is the formula for all n. I want a mathematical proof. So the way we go about this is called a proof by induction. It has two parts, and it kind of takes a little, you just have to think about it, and then you go, oh yeah. So we have some statements like this, right? So P sub n is this statement, sum from I equals 0 to n of n over n plus 1 over 2 of 5 equals n over 2. We have a bunch of statements, and we want two things. We want to show that this is true for some anchor. Doesn't matter where, but in this case we're going to have P1. So P1 is the statement from I equals 0 to 1 equals, well, let's see, 1 times 2 divided by 2 is 1. Oh, it works. This is what's called the anchor. The next part is a little abstract. I want to show that if P sub n, then P sub n plus 1. In other words, you get to assume P sub n, and you just want to prove that it's true for P sub n1 plus 1. Now, that's a little abstract, but think about it. I can start at 1, and then I can show that if 1 is true, 2 is 2. 2 is true, 3 is true. Right? So I proved it for everything. So in this case, how would I do that? Well, P sub n plus 1 would be n plus 1 times n plus 2 over 2. squared plus 3n plus 2 over 2, which would be n squared plus n over 2 plus 2n plus 2 over 2. Well, that's just n plus 1. So I've shown that, which is that right? That just shows that p sub n plus n plus 1, right? Well, that's just what n p sub n plus 1 is, right? We just added the next number. This is useful in math. I'm going to give you an example here. There are other kinds of proofs. This is kind of an uncommon proof. Use it a lot in number theory. It comes up in calculus. There's other types of proofs. There's a direct proof, where you just kind of show from step A to B. And then there's a proof by contradiction. You kind of know these. Okay. So what we want to show is that if f of x equals x to the n, that the derivative of x is nx to the n minus 1. Not just for some n, for every n. We already saw it was true for, well, we've already seen it true for 2n, for two values of n. So f of x equals x, and the derivative is equal to 1, right? Well, 1 times x to the 0 will be 1. We've also seen for f of x equals x squared, f prime of x equals 2x. Well, that's just 2 times x to the 1. Okay. So we already have our anchors. So what we want to show is that given that the derivative of x to the n is n to the x to the n minus 1, keep those parentheses, we want to show that x to the n plus 1 is n plus 1 times x to the n. That's our job here. Well, let's take a look at this. Put in the derivative there. Yeah, derivative. So we want to find out what the derivative of x to the n plus 1 is, which we can write as x to the n times x. Derivative of x to the n times x. Well, now we have a product rule that tells us how to do that, right? It's the derivative of x to the n times x plus x to the n times the derivative of x. Well, we're assuming that this is n x to the n plus 1 times x. I'm sorry, this 1. And this is just 1. All right, x to the n minus 1 times x is just, now we got x to the n plus n, and this is just n plus 1 times x to the n. This is exactly what we needed to show. So now we know this is true for all integers on Earth. All right. It's time to actually use some of this. some function, e for polynomial. It's 12 x cubed minus 6x minus 2. What is derivative of p of x? So shortly, you're just going to do this in your head. Maybe you already can do it. I'm going to be very explicit about using these rules. You're just going to use them without thinking. So here I have 12. So the derivative, here I have a sum, right? So the derivative of the sum is the sum of the derivative. So this is just here I have the derivative of 12x cubed. Well, remember, we didn't put it here. I guess we should put it here. Derivative of k times a function is just k times the derivative of the function. Okay? So I can move this out. So this is 12 k cubed minus 6 derivative of x minus, well, we can just go ahead. We know the derivative of a constant. That's up here is 0. All right, now we can use our power rule. That's what we just proved. So x cubed, that's 3x squared. X, that's just 1. 0 goes away. So we have 36x squared minus 6. You are not going to go through all that. You're just going to look at this and you're just going to say, oh, 36x squared minus 6. Done. A little practice. Let's try that. P of x equals 1/4 x to the 4th minus 2x squared plus x plus 5. What's the derivative? Well, this is going to be 4x cubed times the 4th is just x cubed minus 2 times derivative of x squared, which is 2x, so minus 4x. Plus 1, done. Is that easy? You're going to get good at this. Yes.
Isn't it x cubed?
All right, yes. Write down yet another. Thank you. I don't know, maybe that's only half, because I said x cubed, didn't I? And I wrote the wrong. See, my hand is not very smart. It sometimes has a mind of its own. I understand that completely. Some split brain thing. Oh, you're right. Anybody here, I don't know what field that would be in. I guess medicine, neurology. No, there are people who, in order to stop seizures, they cut this connection between the two hemispheres of their brain. And then they actually, they work together, but it's like they have two different individuals in there. They don't communicate. I don't think I've never had an operation on the brain. Okay, there's another question. We said earlier the same thing. Somebody else? All right. Okay. This has a name. This is called the power rule. All right. We getting close? Yeah, you know what? I could finish this off, but I don't want to. I rush too much. Just leave it there.